I'm going to give you 10 more seconds. Write down what you see. All right. Miss Jody, can you get us started? What did you say? What's one thing you noticed about magnets?
You said it's red and gray.
It's red and gray. What else you got? Angel, what else did you say? An S and an N. Do you know what the S and the N stand for? South and north. What else do you know? What else did you see or what else did you observe? Michaela, what else did you guys say? That's all you said? Beth, what did you say? It's a rectangle. Do all magnets have to be rectangles? No, this one is, but not all of them have to be. Absolutely. Any other things that you noticed about it? What's it made of? It's made of metal. Yeah. Can a magnet be made out of any kind of metal? I think so. I'm not sure. Does anybody know what most magnets are made out of? What kind of metal? There are two big ones. That is a good guess. It is not correct, but it was a very astute guess. I appreciate that. Iron. Have you heard about iron recently, like yesterday, or in the last few days in this classroom? Oh, so that's interesting, and maybe that's kind of why we're talking about this. So magnets are often made of iron. The other thing that they're often made of is nickel. Have you heard about that one too? Yeah, also in the center of the earth. Yeah. Question for you. Is it possible to take a magnet and cut it in half and just have your North Pole? Can I just go to the store and buy a North Pole magnet? How about a South Pole magnet? No, why not? Anybody know? What happened if I got the saw out and I chopped it in half? Yeah, the other side is just going to be the other thing, right? So if I cut it off and I look at this one that says N, and I looked over here, this would be a South Pole, right? That's another important thing to know about magnets. Not something you can really see, but something that's important to know, and that is that they always, let's see if I can spell better, have two poles. Always have a North and South Pole. All right, we're about to move on. I would like for you to take a moment to draw a picture of your magnet in that box. Go ahead and do that right now. Haley. I'm going to give you this piece of paper too. I'm going to have you jump in here. Okay. All right. Once you have drawn that picture, I want you to send the next oldest person up. Leave that magnet at your table. Send the next oldest person up to get a couple more magnets. Come on up. You're going to get one set of magnets here, and you're going to get one triple magnet also.
Oh, it's a bit heavy.
I know, right? It's exciting. All right. I'm going to give you a minute to take a look at these magnets now. You've played with, you've dealt with magnets in school before, you know how they kind of work, but I want you to explore them a little bit. You got a minute. Go, go, go. Open it up. Oh, wow.
Is this supposed to open?
Yeah, you should be able to just pull it off. Yep. Open it up. Brand new magnets. So exciting. How do they interact?
Do we have to keep the piece of white in the middle?
No, you can take it apart. Take it apart. Just take the magnet out. Thanks for asking them. How do they interact? Do some science.
Whoa.
Make some observations. What do you see? Make sure everybody gets a chance to play. Don't be that pushy person that takes all the stuff. Share the fun. Whoa, that's cool.
You're so powerful.
Oh, I love it. I love it.
So opposite ends are trapped and then center ends are propelled.
All right. Time's up. We'll have more time to play with other things in just a little bit. But I would like for you to tell me, what did you observe? Elena, what did you observe?
That opposite ends attract and the same ends repel. So like north and south, like go together, and then south and south will like.
Okay, so I'm gonna use the word poles instead of ends. Is that okay? But yeah, opposite poles attract. What do you mean by they attract? What does that mean?
Like they stick together.
They stick together. They're drawn together, right? If you have not yet seen that, I want you to try that out with the little bar magnets. Take a north and a south pole and put them next to each other. Do they kind of go together? Yeah.
South and south go together.
South and south go together?
Hey, who's that? Yeah, Chief called that.
You know, I think that this magnet is just not super.
Bitch, Cargo, come look at this. That is science. Yeah. Cargo.
Yeah, I think that the painted magnets are not super strong. I think that's the trouble with them. But if you do, that's an interesting observation.
That's good.
It's Cargo.
But these magnets are good. What's up?
Look at this.
What are you doing? Are you doing science?
I'm science.
What? What are you doing? Let me see. Whoa, you're like levitating your magnet. Oh my gosh. All right. And when you use magnets that are, you know, worth their weight in magnetism, Michaela, what do you see if you have like poles? What should they do? Yeah. All right. Are you doing okay over there?
That scared me.
Okay, be careful. Don't abuse the equipment, please. So you've got opposite poles that attract and like poles that repel. Can you draw a picture of that? How might you draw a picture of that? Any idea? How might you draw a picture of that? If I put a north pole and a south pole next to each other, what's going to happen to them? They're going to go together. So maybe I'll use some arrows to indicate that they're going to go together. Right? But if we use good magnets and we put a south pole and a south pole together, then what should happen? They're going to go away from each other. So much so because those magnets are pretty strong. The little ones, right? You can get things to stand up on end. You can, you know, all kinds of fun things. All right. We good? You're going to hold on to all those magnets because we're going to use them for the next thing. I'd like you to send the next youngest person, probably the youngest at your table, unless you have just two, and then you're just going to send the next person up. I know! You're getting your steps in today. 5 paper clips. 5 paper clips per group.
5?
5.
Go ahead and get out of here.
You can dump them out into the bin if you want.
That is for 5. Wonderful.
What we got, boss?
I'm going to give you a couple minutes to interact with the paper clips and the magnets. Probably you've done this before. I've given you enough magnets now, enough paper clips that everybody can kind of get their hands on them. Okay? See what happens. Investigate.
Oh.
Don't just let somebody else do it. What's that?
Yeah.
Did it work on the other pages?
It should be magnetized.
Jumping magnets.
There.
All right, everybody should be interacting with paper clips and magnets right now. Take some time to do that. What are you doing? Strong. Look at you and your ultimate strength. Not this okay. I'm just gonna break this, okay? All right. How are we doing? Wait, do that again.
They travel through each other.
That was funny. Wait, what?
They travel through each other.
What is they? Can you use some more scientific words for me?
Paper clips. It's a magnet thingy. It makes these stick together even though it's not connected to the magnet.
All right. So, Colin, will you carry that up here? Just like that.
Wait.
Ladies and gentlemen, I'd like for your eyes to be up here because we're going to draw this picture.
Alright.
All right. Actually, you know what? You don't have to come up here. Why don't you just walk around and show everybody? See if you can do this too. Draw this picture, friends. Draw this picture. I don't think it's going to hold. Whoa, please be careful with the magnets, okay? Thank you.
Alright, well. Alright.
Draw that picture. Try it out yourself. I bet you've already done it. He's just the loud one, right? I know, but you know what the thing is? We're doing this fast because after this,
I've already done this call.
you gotta be aware of personal space, man. We're gonna get deeper now. We gotta start somewhere, right? Because maybe not every single kid has had the wonderful opportunity to go to science and elementary school and middle school. So we gotta like level the playing field. Are you with me there? Or every year?
Yeah.
But so this year we're gonna actually go deeper, like literally into Earth. See what we did there? Yeah, I know, right? All right, so here you go, ladies and gentlemen. You got a picture. Now, this is the deeper part. Elena's like, I do this every year. Like, oh my gosh, every year in science I do this. So now, I'm just totally teasing you because that's not how you sound, I'm sorry. I want to know what is going on. Not just, oh, it's so cool, look, I have science. Why? Why? Why does this happen? Or tell me what happens first. What are we so excited about? The paper clips what? So the paper clips stick together. And why does that happen? Go.
So paper clips aren't magnetic just like by themselves, but you can
Magnetize?
magnetize them and make them stick to each other.
Awesome. So the paper clips become magnetic in the presence of a strong magnet. So the paper clips themselves aren't magnets, right? And you can't make a paper clip a permanent magnet. It doesn't work that way. But in the presence of a strong magnet, a permanent magnet or an electromagnet, you can make paper clips become magnetic. I want to show you a picture of how this works. Because yes, you've been doing this since you were in kindergarten and preschool and stuff like that. But I'm not sure, and maybe some of your teachers have shown you this, but maybe not. So I just want to see if we can see how this works. Things that are magnetic, okay? Metals that have magnetic properties, inside them, really what they have are little tiny magnets. Little itty bitty magnets. And those little itty bitty magnets in your regular just paper clip that's just sitting there are like this. Do you see this? All these little magnets? Is there any natural arrangement to these magnets? No. They're just kind of whatever. In the presence of a strong magnet, What happens to those itty bitty magnets inside this metal? They what? They organize, right? They're like unionized, right? They're like, let's go, or something, right? They line up. And when they do that, then all of these little itty bitty magnets inside become stronger, don't they? There's like some sort of big philosophical statement right in there, right? Okay. When you organize, you become stronger. You can become a magnet too, right? Oh, that's beautiful. That's so cool. Let's write this down. I want you to write this down on your sheet. Okay. In the presence of a strong magnet, the little magnets inside, please turn that phone alarm off and please put that phone away. Okay? I really don't want to have to call the office, so let's not do that. Little magnets inside line up, okay, to what was I going to say? Little magnets line up to make the material magnetized. Okay. And sometimes it takes a little time for those little tiny magnets to rescatter after it's outside of the presence of a magnetic field. So sometimes if you play with these, you can pick up other paper clips and then move the magnet, and you can still do it for just a little bit. But eventually they just kind of, get all random again, and then it doesn't work out. Question for you. Do all materials have that property such that in the presence of a strong magnet, they line up, they organize? What evidence do you have for that, scientists?
Me.
You?
I'm not sticking to it.
What do you mean? Oh, you're not sticking to it. That's true. Me, it's all right. Yeah. Other examples? So that one example disproves the theory, right? So that's exactly right. You're absolutely right. Other examples, Jacob, did you have one? Wood. Yeah. What else? Table. Paper. Beth, you had your hand up, or you were going to. The table. Yeah. So there are lots of things that don't have these little tiny magnets in them that can line up, but a lot of things also do, and those things are things that are able to be magnetized. Does that make sense? Questions? Are we good? All right. I would like you to send, I think we're on the oldest person, send the next person up. Please bring, guys, listen up. Shh. Please bring the paper clips back. Leave the magnets at your table, but bring the paper clips back.
Oh, wait, no.
Bubble wrap. Oh boy. Now it's really gonna move.
I know. Watch out. Oh, she's fabulous. Wait for it. There should be one more group. Where's my last group? Oh.
Miss Carving, are those things that you draw in that?
So yeah, it's kind of like that. Like you can buy it at the dollar store or whatever. Yeah. There you go. All right. So ladies and gentlemen, may I have your attention, please? Shh. I want you to be careful with this. This is not something that you want to drop or mess with. So set it on the table. I'm going to give you a couple minutes to do some investigation, and then we'll talk, okay? So make sure everybody's got a chance to investigate, to play, to find out what's going on.
You just scratched it.
Be careful. All right. So you have an opportunity now. You broke it, Hayden?
No.
I didn't break it.
Child. Hayden, do you have siblings?
Me?
Yeah.
No.
You don't like child? Yeah. That was not a loaded question. I was just curious. All right. So, when you place the magnet on top of this funny plastic box, you notice that there are things that happen, right? Does anybody know what's inside this box?
Magnesium.
No, it's not magnesium. You guys are all excited about magnesium. Magnesium is not magnetic. Nope. Nope. Does anybody know what else? Anybody else want to give a guess? It is. It's iron. They're iron filings. Yes. So literally, like when people are in the shop and they're cutting iron, it's kind of, if you cut wood, you get sawdust. It's the iron equivalent to that. Okay? And you want to know the funny part of it? Is that for machinists, scientists, can I have your attention for just a moment, please? The funny thing is that for a machinist, the iron filings are just trash. But for science teachers, we're like, yes, we will pay lots of money for your little trash. Like, one person's trash is another man's treasure. I don't know, something like that. That's what we're talking about. So they put these iron filings, these little bits of iron, into oil so that they're suspended and so they can move. And when they do that, what do you notice? What happens? You can see that those little pieces of iron become magnetic, don't they? You see that? The iron is just like those paper clips were, right? Same kind of deal. The nice thing about this little board is that you can kind of see patterns on it. So if you has anybody ever played with an Etch-a-Sketch?
Yes.
Yeah? An Etch-a-Sketch uses exactly this technology. Okay? Inside an Etch-a-Sketch, you have iron filings. And when you twist the knobs, you're just moving a magnet. That's literally what you're doing. Okay? If you've ever done the little thing where you've got, you pick up and you put like the hair on the little, the person, right? Same darn thing. It's all the same. Right? There you go. Magnadoodle, same thing. It's all the same thing, you guys. It's all this technology right here. Okay? I want to write down what we see here. So what did we say is inside this? Iron, little pieces of iron. Iron filings in oil. And those little pieces of iron, when you put them next to a magnet, what do? They become little magnets, yeah. They become magnetized, okay? The filings line up with the poles, just like the paper clips did, okay? And the funny thing about this is that if you look very carefully at the picture, and I'm going to show you a nicer picture than I can generate right in front of you, you can see these really lovely lines. Do you see that? How the iron lines up very nicely, okay, all across there. So that's kind of cool. What's that? The reason is because when the way that they made this one, the iron filings weren't in oil, so they were able to move a little bit more easily. Does that make sense? And they had a stronger magnet, which is why it can do that. It's just hard to see it because the oil is in there. But you can kind of, if you set your magnet down, you can kind of see at the poles that they kind of star out. Like this part here you can see, right, Hannah? Do you know what I'm talking about? Yeah. So it's a little harder to see. That's why I wanted to show you this picture as well. All right. So they become magnetized, and you can see lines, and those lines have a very specific name. So this is another one of those things that maybe you didn't talk about when you were doing this in third grade, or maybe not in preschool. I don't know. Maybe you did in preschool because you had a really, really nerdy preschool teacher. I don't know. But the lines that you can see, does anybody know what they're called? We're just going to look right over here. Ding, 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 ding. They're magnetic field lines. Okay. In that space for a picture, what are you going to draw? A picture. of the lines. So draw yourself a magnet with a north and south pole, and then go ahead and draw those lines. So the lines go out from one side and into the other side. So go ahead and draw some lines. Once you got that drawn, you can leave that oil board at your table, and I'd like you to send the next person in line up to come get a couple of, let's do 3 compasses. Come on up.
How many?
3.
3.
Oh.
Are you happy now?
Okay, how many? Oh, I said my
3.
circle is better than his.
Oh.
Yeah, but I spread it all out on the bottom. That's way lower. Okay. A lot.
Okay.
All right. How many of you have ever used or seen a compass before? Yeah. What is a compass? It tells you where the North Pole is. How does it do that?
Magnetic field.
Oh, look at you guys all talking all fancy. I love it. I love it. I'm going to get my compass. And I want you to use your permanent magnets, the ones that you have, your little bar magnets. And I want you to just kind of experiment and see what happens. Whoa! That's interesting. If you put the south pole down, then you can get the red one to point to it. If you flip it around, whoa! Whoa, 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 right? How does that work? Why does that work? Is a compass magic? No, you will learn quickly from me that nothing is magic, right? Everything is
Science.
Science, and even more specifically, usually it's physics. Yeah, so it's not magic. It's science. Science. Yeah. How does a compass work? If I was going to ask you to make me a compass, what would you do? What equipment would you need to make a compass? Anybody know?
A paper clip.
A paper clip? Okay.
Oh.
Anything else? So if I just hand you a paper clip, can you make me a compass?
Water.
No. Sydney, if I was going to ask you to make me a compass, what would you ask for? What do you need? You need a magnet, don't you? Yeah. All that a compass is, ladies and gentlemen, is a little tiny magnet that's put on a little point. Okay? That's all it is. It's just a little bar magnet on a point so that it's able to rotate and spin. And then just like when you've got 2 magnets like this and I can get this one to move, you with me there? Like, whoa, it's not magic, it's science. Right? If this is up on a point so that it can just rotate, then it's just going to rotate anytime it wants to. Same kind of deal. So let's write that down first, and then we'll talk about how it relates to our magnets. Okay? So a compass, okay, is just a very small magnet that is free to rotate. Okay? When it comes near a bar magnet, what happens to it? You were there, but you just like stop talking. What does it do? If I have my compass and then I bring my bar magnet next to it? That's exactly right. It's attracted to the magnet, right? It rotates so that its north points to the south and its south points to the north. Yeah. Yeah. So near a bar magnet or any other permanent magnet, any magnetic field in general, really, okay? It rotates to align with the magnetic field. I want you to do one more thing before we move on to the next step. And that is we're going to do a little combination demonstration. So I would like for you to put kind of shake out your iron filing board. I want you to put your bar magnet on top so that you can kind of see where those lines are. And actually, Hannah, you were saying it was hard to see, but you can kind of see the lines here because you can see that those iron filings kind of line up. Do you see that? Yeah. Then I want you to take your compass and I want you to take a look at the way it points. If you put it right at the center, do you notice that it points just along the bar magnet? You've got multiple compasses, so you can put compasses all the way around. You can put one like this and one like this, and you can see that they all line up. But then if you move one, take a look at what happens. Oops, you can't see that because I need to zoom out. Zoom out, zoom out, zoom out. See what's happening?
Whoa, it's like a party.
Right? You make it happen. Do it at yours. See if you can make that happen. Watch how, just like I was doing.
This compass is messed up.
The compass is messed up. Did you break it? Did you see it? Did you move it? No, there you go. So this is literally just a little magnet. It's sitting on a deal.
If someone's gonna get it, man,
Yeah, so we're gonna do that. That's oh no, yes. All right. There's a little picture spot right next to this experiment, right? Draw your picture. Draw it like that. Draw your picture to show that this works. This is in letter E, example E, demo E. All right? Figure out some way to visually represent the fact that as you move this, okay, that arrow moves. Figure out a way to draw that picture. Okay. So the compass follows any magnetic field that it's around. Now this may seem a little bit strange, ladies and gentlemen, but for this next one, what I would like you to do is to move all the bar magnets far away from your compasses. So put them all like towards the edge of the table. I want you to just have the compass out. For part F, really what we're doing is talking about the reasons that we really use. Why do you know about compasses? It's not just to play with magnets. What do you know about compasses? What do we use them for in life? Navigation, right? You use them for navigation. How and why?
The little arrow points to the poles.
Okay. Okay, so that's exactly what I want you to get. So I want to make sure everybody's listening. So I think you kind of get it, but I really want to make sure that you get it. So we use a compass to navigate, right? We use a compass because it's very convenient because it points in specific directions. Yeah? But the reason that works is because the Earth must have what? It has a magnetic field, right? It has a magnetic field that is fairly constant, so we can find our way around as long as you don't, if you're holding a magnet in your pocket and you're trying to do your orienteering, that's a poor choice because it's always just going to point to the magnet in your pocket. Are you with me there? Okay. But if you don't have any other magnets around, then it's going to align to the magnetic field of the Earth. So if you put your magnets far away and then you just look at your compass, then they should all point in the same direction, okay? They should all point towards the magnetic North Pole. It's really funny, the school that I used to teach in, there was some sort of weird stuff in the old pipes or something, so the compasses didn't actually point north because there was something going on in the building. I don't know, it was very strange. But anyway, we know that if you're out in nature, for example, we can use the compass to navigate because it aligns with the Earth's magnetic field. What? The Earth is like a magnet? Does that mean that there's literally one of these sitting in the middle of the Earth? We've been talking all week about what's in the middle of the Earth, and nobody's ever mentioned that there's a big piece of iron that goes north to south. Is that what is really going on or no? No. But the iron that is in the core of the Earth does generate a magnetic field in the same way, but it's not a bar magnet. I want to make that really clear because sometimes people think it literally means that. The picture that I want you to draw with this, though, looks kind of like this, okay? So, what's that? Stuff. So the Earth has a magnetic field around it. The lines of the magnetic field look very, very similar to the lines from that bar magnet that we saw on the oil. It's very similar. It's interesting. Okay? Part of the reason that we're spending a lot of time doing this today is because next week we're going to talk about how we use that in earth science, how we use that to learn about the changes, and how it might change itself. What? See, oh, there we go. That's not quite what I wanted, but that'll work. Okay. How we doing? Doing okay? All right. All right. Last one. Send that last person up. One more thing to come get. Somebody's got to get up. Hey, who's going to be you?
No, I'll get up.
Grab one of the right one.
Shoot it.
So, before you do anything, ladies and gentlemen, I'd like your attention for this. Can I have your attention, please? Thank you so much. So, I just had whoever it was from your group come up to get 2 rocks, and I should have told you what they were about first, so let me tell you that real quick. These are 2 naturally occurring minerals, okay? They are both iron. They both have iron in them, I should say, okay? This one's called pyrite, this one's called magnetite. I want you to do the pyrite first. Now, before we go any further, though, I do want to tell you that any effects that you see are not going to be overwhelming like they are with a bar magnet. So I want you to have a heads up for that, okay? I want you to take the pyrite, the sparkly one, the one that's labeled number 15, and I'd like you to set all the other magnets aside. Just have one compass out. Take that pyrite, and I want you to bring it near the compass. And I want you to see if anything happens. Take a look. Anything interesting? Okay, and I want to remind you that this does have iron in it. Okay? Naturally occurring, sparkly. Does anybody know what this is sometimes called? Anybody know what this is sometimes called? It is always called pyrite. Sometimes people call that, what does it kind of look like? It's shiny.
Tin foil.
Good guess. It looks a lot like gold.
Tell me this doesn't look
Okay.
like gold.
It does.
It's a little golder than that, but yes, this is called fool's gold. If you ever heard of fool's gold, that's what this is. All right. I want you to take your magnetite, also iron. Bring it towards your compass. What do you see? It doesn't move a ton, does it? But it does move a little bit. What does that tell you?
So basically, not all iron.
The things are aligned.
Iron. Say that louder, Jacob, so everybody can hear you. What?
Like the little magnets inside of it are aligned.
You got it. That's exactly right. So inside magnetite, that's what it's called. Inside magnetite, the thingies, the little magnets inside the iron, happen to be aligned. And that has to do with the way that the magnetite was created, and we'll talk about how those rocks and minerals are created and formed and solidified later. But the thing that I want you to be aware of, and the thing that I want you to write down right now about that iron ore samples, coming back here, is that some types of iron ore, I'll say some types of iron minerals. In our particular case, we're talking about magnetite. Okay. Have, we'll say, magnetic properties. What does that mean? It means that the small magnets inside are aligned, just like they were inside those paper clips earlier, right? But they are permanently aligned. So it's more like a permanent magnet. There are some iron samples called lodestone that are really, really strongly magnetized. And they're actually the first type of magnet that we ever discovered or found, okay? They used to hang them by strings to use them as compasses before we learned how to do other things. So you can draw yourself a little picture here of a compass and maybe your little rock, and showing that when you bring the rock, the magnetite closer, then maybe it moves a little bit, something like that. So you get that in your mind and you remember what's going on there. How are we doing? We okay? Yeah? Issues, questions, concerns right now? We feeling all right about that? I would like for you to send one person up. Hold on just a second. I'm going to stop this.